So this lesson is a two-part lesson. We're going to do this over the course of 2 days. We'll start it in the first day and we'll finish the rest of the lesson the second day. There's a lot of content in here and just too much to cover in one day. So today we're going to look at how functions can be transformed, how they can be changed. We did this a little bit last year. We're going to refer back to how we did with quadratics because it's a good starting point for us. You might remember in grade 10 that a quadratic function, y equals x squared, is sort of our standard function. We're going to call that our parent function now. And we could change it. The easiest way to change it by putting it into vertex form by putting numbers in different spots. So we have an a, an h, a k. For example, y equals 2, x minus 3 squared plus 1. And each of those numbers, the 2, the 3, and the 1, did things to that basic parent function, the parabola. And the three things that happened were, a, that thing out front, changed your step pattern. It stretched things. It also reflected things. If it was a -2, it became opening down instead of opening up. We call that a vertical reflection. The h, the 3, moves things left and right. And you might remember you take things out of the bracket, you do the opposite sign. So a -3 inside the bracket actually moves things to the right 3. And the +1 at the end moved things up and down. Okay, +1 moved it up 1. And using this vertex form, we can actually sketch a new function. We used our vertex and our step pattern and made our new dots. Now, we're going to talk about functions in this lesson, so we can't necessarily use step patterns and vertices, but we can use lots of the same ideas for every other kind of function. And I say other kind of function because quadratics are just one type of function. Okay, here's the big note part. So, if we're given some kind of function, any random function, as long as it's a function, y equals fx, and we put a value out front, so a times fx. Just like with quadratics, that a value is going to transform our function, and it's going to stretch it, compress it, or reflect it in a vertical direction. You notice it's all about vertical things here. Here are the three rules. If it's larger than 1, basically a whole number, that's a vertical stretch. So that might be like y equals 3 fx. Now it doesn't technically have to be a whole number. It could be a decimal, a fraction, but it has to be bigger than 1. We're usually just going to do with whole numbers to make our life easier, but I could have 7.5 fx. That would vertically stretch my function by 7.5 times. Okay, that's rule 1. Rule 2, if the number is a fraction, a number between 0 and 1. So for example, y equals 1/2 fx. That's going to compress our function vertically. It's going to make it vertically half the size. And again, it doesn't have to be a fraction. It could be a decimal. And I could have 0.4 fx. That's going to shrink my function again by a factor of 0.4. Okay, as long as the number is less than 1, we have a vertical compression. And the third one is we have a vertical reflection. That's what happens if I have a negative sign out front. It's the negative of fx, vertical reflection. Now, we can combine these things. I could have something y equals -4 fx. And two things are going to happen there. The negative sign is going to be a vertical reflection, and the 4 is going to be a vertical stretch. So two separate things. To describe it, I have to talk about two different things. Now, I talked about we can't use the idea of a step pattern necessarily, but we can use lots of the same ideas from quadratics. In quadratics, we multiplied 1, 3, 5 by the value of a, because those were our vertical values. So when I deal with a regular function, what I can do instead is I can multiply the y values of the original function by a, and I'll get some new y values. And that will create a new function for me. Something that's been stretched, compressed, or reflected in a vertical way. One last little point before we try some examples here. Sometimes you can have points that don't change. They remain the exact same point that they were originally. We call those things invariant points. Okay, so if they don't change, that means they're invariant. We'll try some examples where we'll see some of those. So let's look at the first example here. I've got a function. Obviously, it's not a parabola, just some random function. But what's this random function? I can make a table of values. Okay, I can pick the first point, negative 3, 0. The second point is 0, 2. And the third point is 6 and 0. Okay, and I can use these points to make new functions. Now, if you read the question, it says sketch and then state domain range. So we'll talk about domain range in just a second. Let's look at the first one. I want to do 2fx. What is that? That's a vertical stretch by a factor of, BAFO, by a factor of 2. So how do I sketch that thing? Well, I take my original table, the green one, and I multiply my y values by 2. So 2 times y. What's going to happen to the x's? Nothing. They're going to stay exactly the same. I haven't done anything to the x's. I'm doing vertical stretches. If I multiply the y's by 2, we get 0, 4, and 0. If we redraw that, negative 3, 0, 0, 4, connect them, and 6, 0, I get my new function. We're asked for a domain and range. These are all real numbers. I don't have room, so I'm not going to write the part of all real numbers. I'm just going to write the interval notation. But our domain goes from negative 3 to 6. And our range goes from a low of 0 up to 4. And you can find that by looking at your picture or simply looking at your table for the highest and lowest numbers. Done. That's it. We got a sketch, we got domain range. Oh, one more thing, they ask for invariant points. Remember we said an invariant point is a point that hasn't changed. If you look at the graph, there's actually 2 of them. Which 2 points are invariant? The ones that are on the x-axis. They haven't changed because when you multiply 0 by something, it remains a 0. So one of my invariant points is negative 3, 0, and the other one is 6, 0. And the other way you could have figured that out is by looking at your table and see if any of the points are exactly the same still. And sure enough, the first one and the last one are still the same points. Okay, let's try B. Same ideas, but this time we're going to do y equals 1/2 fx. What's happening with 1/2 fx? Well, because it's less than 1, we call that a vertical compression by a factor of 2. It's half the size. Now, if you wrote down a half, I'd take that too. That's the same thing, okay? Vertical compression by a half or factor of 2. How are we going to get that? We're going to take our original table, the green one, and we're going to take half of y. Or in other words, 0.5 if you want to, if you don't like fractions. What's going to change? Well, not the x's. They're the same still. But the y's, remember we're working with the green table, are going to be half of what they used to be. So if I draw that, negative 3, 0, 0, 1, 6, 0, I get something that's been vertically compressed. Our domain hasn't changed. Our range, it's been compressed. So now instead of going all the way up to 2, it only goes up to 1. Do we have any invariant points? Sure do. Our invariant points are the same ones we had previously on the x-axis. A little hint for you, when you stretch or compress or reflect things vertically, the x-axis points will always remain invariant because you're multiplying by 0. Okay, let's try the third one. Same graph, I haven't changed it, just more space on this screen. So we have the exact same table we had before. Okay, so negative 3 and 0, 0 and 2, 6 and 0. And this time I want to do the negative fx. What is that? That's a vertical reflection. How do I do that? I take my y values and I take the negative of them. So my x's don't change, my y's have the opposite signs now. Again, we have those invariants on the x-axis, they don't change. But when I graph it, it should look like it's been flipped over vertically, and it does. Okay, our domain hasn't changed. Our range, oh, our low is not 0 anymore. Our low is now negative 2. Right, so you gotta be careful with that one. The high is now 0. And do we have any invariants? Sure do. The ones that are on the x-axis. Okay, so those are some vertical things. Now, everything we can do vertically, we can also do horizontally. So this is the second half of the lesson. Okay. Just before we get to that, one little trick for you. Domain and range, sometimes painful, hard to work through, lots of thinking. So a little shortcut, if you will. If you don't feel like looking at your graph or looking at your table to find your domain range, you can look at your original function and apply the transformation. And what does that mean? So let's go back for a second here, if you will. In this green one originally, I didn't list it, but my domain was -3 to 6. My range was 0 to 2. I don't actually need the graph to figure out the domain and range of the red or the blue ones. I can simply apply the transformation. If I were to take the transformation, the red one, and double the y's, that's what the transformation was, I get the range for the red one. If I were to take the blue transformation, what did we do here? We took 0.5 times y. What do you notice about the range for the blue one? Oh, it's half of the y's. I don't actually need the table or the graph to do it. Now, one little trick. If I try that with the reflection one, reflection, this was, we didn't do anything with the x's, but I'll write them down anyways. If I try and take the negative of y here, I don't get the same thing in my range. There's one little challenge there. What would you actually get? You'd get negative times 0 is 0, and you'd get this. But that's not what we have, is it? In fact, what we have is kind of the opposite of that. Well, let's come back to that in just a second, okay? Let's try some things. Given a range and domain, determine the domain range for the following. All right, now, if we look at these questions, we notice we're not touching the domain. We're only doing vertical things. A vertical stretch by a factor of 5. So how do I get my new range? I multiply everything by 5. Done. Domain would be the same. Okay, we try the B one. What are we doing here? We're doing a vertical compression, because it's less than 1, by 3/4. How would I get that? I'd have to take 3/4 of y. What's 3/4 times -2? That is -1.5. Done. Quick, right? We don't need the table. We don't need the graphs. I can apply transformations. But here's the tricky one. Letter C. What happens when it's a negative? Okay. We noticed there was a little problem in this previous one here, this negative sign. It wasn't quite the same, right? In fact, if you think about it, this thing needs to go here, and this thing needs to go here. Now, how can we take that into account? Here's a little rule for you. Okay. If you have a negative one, it doesn't matter if it's a fraction, a whole number, if you have a negative one, right, when you multiply by the negative, the inequality will change directions. What does that mean? If we go back to that previous one, instead of swapping spots, what if we swapped the directions? Isn't that the same thing as that? Right? So a little bit less confusion there. You multiply like you normally would, but just change the directions of your inequalities. So if we try this one, and what's happening in this question, we're doing our two things. We've got a vertical reflection, the negative sign, and we've got a vertical stretch by a factor of 2. Okay, what do we need to do? We need to take this and times it by -2. What would that give me? -2 times -2 is 4. It's a negative sign, so I'm going to flip my inequality other direction. Why? And what does that mean? You can write it that way, or if you want to, just we're used to the way we're normally seeing it. Oops, wrong order. Y is less than 4. Okay, so that's a little trick for you. Domain range, don't need the table, don't need the graph. We can do it much faster, much smarter by applying transformations. Just be careful for the reflection. You change the order of your signs. Okay, back to what I was saying about the horizontal thing. So here's the second half of the lesson. Everything we do vertically, we can do horizontally. The only trick is the letter, the number appear in a different spot. So in a horizontal translation, or sorry, a horizontal reflection, compression, or stretch, we put the number inside the bracket, but in front of the x. And the trickiest thing of all is anything that affects x's does it in the opposite way. So what does that mean? Well, if it's a fraction this time, so let's say f at 1/2 x, it's actually going to stretch things. If it's a whole number this time, it's actually going to compress things. And if it's a negative, well, a negative actually does the same. It's a reflection. So these are all horizontal things. So how am I going to do the math for this? This time, instead of multiplying, because I'm doing the opposite, I'm going to divide the x values by k. Okay? So we'll try some examples again. Get the hang of this. The big thing here to remember is the opposite operation. Things that do x's do opposites. So let's start off with the table, like we did before. X and Y. Important points. We have 5 of them this time. Okay, everywhere we change direction is kind of important. Okay, and we might as well use our shortcut idea for domain range. So my domain, look at my table, goes from -4 up to 4. In my range, I have a low of 0 and a high of 3. And that sure enough matches my graph. Okay. What are we going to do first? I'm going to do a horizontal, it's inside the bracket, reflection. How do I do that? I take the x's divided by k. So I'm dividing by -1 this time. What's going to happen? X, Y. My x is divided by -1, so I've got a +4, a +2, a 0, a -2, a -4. 0, 2, 0, 3, 0. Okay, domain range. If I divide my domain by -1, I'll get +4, swap the sign, -4, and swap the sign. Now you can write it that way, which totally makes sense. Or if you put it in our normal format, the small one goes on the left, and the big one goes on the right. And all I do is change the order around backwards, okay? Still means the same thing. Our range hasn't changed, 0 to 3. Let's graph it and see if our domain range actually makes sense. So my first point is now 4, 0, then 2, 2, join them, 0, 0, join them, -2, 3, join it, and -4, 0, join it. And there's a horizontal reflection, a mirror down the middle. My domain goes from -4 to 4, yep. My range goes from 0 to 3, done. Okay, let's try B. In B, what am I doing? It's going to be a horizontal. It's a 2, which means I'm going to divide by 2. When I divide things, it's going to be a compression. And we said our rule was whole numbers are compressions for horizontal things. Okay, let's take our red table again. Divide everything by 2 for the x's. So -2, -1, 0, 1, 2, and 0, 2, 0, 3, 0. Our domain, you can divide those x's by 2. So we'll go from -2 up to +2. And our range, and let's graph it. -2, 0, -1 and 2, 0, 0, we can join them. 1, 3, and 2, 0. And it's a horizontal compression. My domain matches, my range matches, it's all good. It didn't ask us about invariant points, but there would be one, right? The number 0, 0, that point. All right, last parts. Put it all together again. Same picture, just gonna do some more fun things with it. So let's rewrite that table again, just real quick here. -4, 0, -2, 2, 0, 0, 2, 3, 4, 0. My domain, -4 to 4. And my range, 0 to 3. Okay, what are we gonna do this time? Ooh, a third. So I need to take my x's and divide by 1/3. Huh, that's interesting. So here's an idea for you. When I divide by a third, if you remember fractions, that really means we're multiplying by 3 over 1. Or in other words, x divided by a third equals 3 times x. Those are the same things. Okay? Hopefully that makes sense because in our description, we said a third fractions actually stretch things. So this would be a horizontal stretch by a factor of 3. It's actually 3 times as long. So if we triple all our x's, we'll get -12, -6, 0, 6, and 12. And these ones are going to stay the same. Now, I can't actually fit on my graph. I'm sorry. I'll do our best here and get the idea, but this graph's going to go that way, okay? 0, 0, 6, 3, and then 12, 0 will be somewhere like over here, right? So we'd have to think of it that way. It's been a horizontal stretch by a factor of 3. We can apply that transformation to our domain. Let's triple it. And our range will stay the same. Okay. Yeah, so that's another idea there. The idea of when you divide by a fraction, you actually end up multiplying. So dividing by a third, multiply by 3. Divide by a half, multiply by 2. All right, last one. I got two things going on in this one. What's going on? I've got this 2 is a vertical stretch. Right? Vertical things do what they look like. This 2 is a horizontal compression. Okay? Things that do the x's do the opposites. So it's going to be our big idea to try and remember. X's are the opposites. So when I do my table this time, I got to change my x's and my y's. Make sure you're working off the red table, okay? X divided by 2 and 2 times the y's. So -2, -1, 0, 1 and 2. And double the y's, 0, 4, 0, 6, 0. Let's do our domain right now, so half the x's. And let's do our range, double the y's, and hopefully that will match our picture. So -2, 0, -1, 4, 0, 0, connect them. 1, 6, let's go off top of my graph up there, and 2, 0. And there's our vertical stretch, horizontal compression at the same time. Okay, if we asked about invariant points, the only one we would have would be 0, 0. Every other point is different from our original table. Okay, so that's, as I said, a two-part lesson. Okay, the vertical stuff will all come the first day, the horizontal stuff will come the second day. Our homework for this comes off of a sheet. Okay, we're going to do the first couple of questions off of it. I think we're going to do numbers 1 through 5 the first day, or sorry, the second day. The first day you don't have any homework. You can just get the ideas in and time the second day to work on things. So 1 through 5 off the handout, stretches, compressions, and reflections.